Welcome everyone, dear friends, family members, and also my members of the Thesis committee. Today I'll present you my thesis, which is PyHintSearch, which is a validated combinatorial search for probabilistic type inference models. Today, the outline of my presentation, I'll start with an introduction, then I'll discuss the search strategy. Next up is the PyHintSearch tool that I developed, an evaluation of this as well. Next are the results, and finally we will conclude. So first, the introduction. Although research is very difficult, I would like to start off extremely simple. What is 1 plus 1? Anyone?
2.
2, exactly. 2. Now, this operation can be described as a function in Python. You have the add function with parameters x and y, and you can add these together. If we give this function integers 1 and 1, it returns 2. But this function can also work on strings. If we give it hello and world, it concatenates these strings, returning hello world. But which operation do you expect? Well, as a software developer, you might look at this and usually the function name gives it away, but we can also annotate the function. Annotations are as follows. You can specify the parameters of your function, as well as the return type that you expect the function to return. And these annotations, the places where they are filled in, is called a type slot, which I would like you to remember. Next up is the static type checker. And type-ins, these type annotations are useful for static type checker. And I used PyWrite, the static type checker. And PyWrite has many functions, but the 3 important ones for my thesis are type checking, type inference, and type validation. First of all, type checking. We now have these type annotations specified. If we then give the function hello world to strings, this does not match up. A string is not an integer. So PyWrite says, no, that doesn't work. If we do specify correct integer values, then it agrees, it works. That's type checking. As for type inference, you have type propagation and type, inference. Propagation is we have a function and it is annotated, and if other functions also call this, the types are propagated to the other functions as well. As for type inference, well, you can think with me. We have an integer and an integer. What should the program return? Well, PyWrite would infer that it also returns an integer type, based on analyzing the code. Lastly, we can do type validation. We can exploit PyWrite for validating type annotations. If we have, once again, the add function, and now we annotate it to return a string. Well, as we've seen before, it should actually be an integer, but now we try to add a string annotation, and PyWrite complains. It doesn't work. And this is exactly what is used for the validated combinatorial search. We can type check these annotations that we are adding. Now, the next practical part of my project is probabilistic type inference models. These models, if you give them code like this, which is unannotated, but you can just see the type slots which need to be filled, they give a prediction which type to fill into the slot. For example, it returns these 3 annotations, and similarly for the second and the last one, it gives even more predictions. It returns 5 predictions. Now, let's take the first ones of these and fill them into the slots. As you can see, this combination does not work. That's too bad. But we have all of these predictions. So how do we actually find a combination that suits the code? Well, here you have 3, you have 3, you have 3. If you have many more functions and many more available type slots, you have way too many options. It grows exponentially. But well, for this one, I'll provide you with the answer. We choose the integer values, we fill them in, and it works. So, how do we find a valid combination? Related work focuses primarily on predicting accurate type annotations that these models give back. But they cannot guarantee the correctness of the predicted types, like we just saw while filling it in. Now, my professor, Georgios, Gousios, worked on a typewriter paper, which was released in 2019, which also works with type annotations and a validated search. But by now, their machine learning model is outperformed by other works, and the search-based validation cannot correct wrong types that were added. It can only filter them out. And you also have to wait a long time for feedback from the type checker, as it is written to disk before being analyzed and the feedback is returned. So, I identified identified the following research gap. We need a fast search strategy to validate combinations of predicted type annotations for Python code, to ensure their validity within the context of the code base, and to increase the total number of annotations. And this is where PyHintSearch, my develop tool, comes in. Originally, we have the project code, we give it to PyWrite. PyWrite looks at the code, analyzes it infers some types, and fills a couple of type slots. But not all type slots can be filled this way. Now, in this new situation, we do the same. We still give it to PyWrite, but for the remaining type slots, we have the machine learning model determine and predict types for this. And then to find a combination that is actually valid in the code, we need the validated combinatorial search. And with this, we fill many more slots, basically almost all, which I'll present. Now, this brings some research questions with them. First of all, on the coverage. What is the overall increase in the number of type annotations when combining static type inference, like PyWrite, with a machine learning model? And secondly, what are the performance characteristics in terms of speed, memory usage, and scalability of the PyHintSearch tool? Lastly, how does the presence of type annotations impact downstream program analysis? And I'd like to give you the answers in today's presentation. But first, let me show you the search strategy. We have this function with the predictions. If you take the top predictions, that's called the top one. If you take the top 3 predictions, we can use those as, well, the top 3, and this can be used to create a search tree, which I'll show you soon. The more annotations you use, the bigger your search tree becomes. So, for example, we have 2 functions. We have foo and we have bar. And notice here, the foo function is also called inside of the bar function. So they are dependent on one another. These functions have the type slots, and the machine learning model for the first one predicts a string and an integer. For now, the probabilities are excluded, but you can represent this as a node with 3 outgoing edges. You have the string edge, the integer edge, and the empty type, which if you fill it in, you don't fill in the type slot, but that's also valid. And next, the second type slot has these 3 predictions, which we can concatenate underneath. So this node and that node and that node are the next predictions. And similarly, for the third type slot, we do that underneath, and thus we create a larger search tree. Now, let's search for a combination. First, we always start going to the left side. We start with filling in a string. We fill in the string in the type slot, and 3 times a string value, well, then you would expect to return a string as well. And this works. Cool. We fill in the integer, and now it should return an integer. But we just assumed that it returns a string. So an integer, that does not work. Okay, then a float. Well, similarly, float doesn't work. A list of bool, well, list of booleans also doesn't work. So the last option we have, we try the empty type. We fill in the empty type, and the empty type, that works, because it is inferred to still return a string. Okay, let's continue to the third type slot. We fill in an integer in this case, but here you can see that an integer is the x parameters given to the foo function, and the foo function expects a string, but now you would expect to give an integer. So this does not work either. Similarly, for a boolean, same case, and list of float also doesn't work. Well, then maybe filling in the empty type would work, right? Well, if we fill it in, then yes, the foo function accepts x, but foo returns a string, which is inferred. And number is now a string, and 42 plus a string is actually a string. And we say that it should return an integer type. So this doesn't work either. Okay, so now we have tried all the options. What next? Well, we can go back up the tree, trying to redo annotations that might have not been correct. So we move up one level, but we also tried all these predictions. So we move up another level, and we try the integer type for the first type slot. We fill in the integer type, 3 times the integer value still returns an integer value, so that works. Then we fill in the return type. Well, yes, this is an integer value. And then lastly, for the third annotation, we also fill in an integer value. And yes, that works as well. And great. Now we have found a valid combination of type annotations that fit the code. And again, let me show you the tree, how it moves. and we find a combination. Well, this is where PyHintSearch comes in. This is the tool that I developed, and it consists of 7 components, which I'll discuss now one by one. First, gathering project-related types. Assume for a second that you are my tool. You get a prediction from a machine learning model, and it just says, it's a tensor. What can we do with this? Well, tensor is not a built-in type in Python code. It needs to be imported. So therefore, we first have to gather all the classes from the local files, because a class can be used as a type annotation, but also Python code can have dependencies. And dependencies also have classes, so we also need to gather these, and dependencies are often defined in a virtual environment. So we gather all these classes to ultimately import a class that well, we can use, like the tensor class. The second component is PyWrite stub files. You still remember the inference by PyWrite? We have an integer and an integer, and it infers it to be an integer. Well, we have a command for this, which is PyWrite --create stub. It creates stub files with invert types. And a stub file is in essence just the function header with type annotations added and no definition of the function what it does. And the invert type is added as a comment last. Now, we can parse these comments to extract the PyWrite invert type, and then we can integrate these type annotations into our original code. Now, this is nice, but there's no need to search for the initially provided annotations that a developer gave, and now these invert type annotations as well. Why? Well, these type slots have already been filled, so we can exclude those. The fourth component is the machine learning model. We have my tool, PyHintSearch, is machine learning model agnostic, meaning that any model that give predictions would work. The only requirement is that the predictions need to be in a specific JSON format to be parsed and be used. We have 2 models. The first one is type for Py, and it was developed here at the TU Delft. It has an API endpoint for the predictions, which is very nice for prototyping the tool to see if it works. It is also quite fast, and it does predictions per file. So if you upload a file to it, then it gives the predictions back for that single file. The other model is type T5. It was a state-of-the-art model when I started implementing my tool, but this one only gives a single prediction back instead of multiple ones. This one also works on a complete project, so not single files, and the return, it returned predictions, but it wasn't in the correct format that my tool needed. So I also created a Flash-based web API for this, and this is called Type T5 API to actually be used by my tool now. The fifth component is the language server. And PyWrite's language server is used for the fast feedback on checking the validity of an added type annotation. We use the language server protocol to talk with the server, and usually this is actually used to work with a code editor to provide syntax highlighting or code completion, but we kind of fake being a code editor by sending commands like, hey, we would like to open a file, we would like to change the contents of the file, and we'd like to close the file, and then we receive diagnostics back from the server, indicating whether if adding an annotation, for example, is valid or not. And this is just an image showing my tool on the left, the server on the right, all the communication between these, but the most important ones are over here, that for each file we open it, and for each type annotation that we try out, we send a did change notification to get feedback. Well, the validated combinatorial search I already showed you. It is implemented, and do you still remember the search tree? It looked like this. But if you look closely, you see that these nodes are exactly the same. And similarly, for all of these nodes, there are duplicates. And storing this access information, well, that isn't nice. So we store it in a dictionary. We just have, for each layer, we store the predictions, and then using a 2-pointer system for search, one for the current layer we are at, basically the type slot we are visiting, and we have a second, which is a list of indices for the current prediction for each layer. And with this, we can track at which node we are actually trying a prediction. This looks like this. We have a dictionary. This is the first pointer, second pointer. If we try to visit the next prediction, we increment the pointer one by one, and go to the next layer, we increment the other pointer. And with this way, we can, well, we use less disk space for duplicate nodes as well. The final component are stub files creation. Now, after searching for combination, we have a program with type annotations. Great. We can save this as a fully annotated source code file. So just the code and the annotations. But modifying original code is not always desired. It could, for example, be that it's someone else's library. So we would like to save our program as a stub file. Just the definition with the annotations. So it can be used by a tool, but we don't overwrite original code. Well, now the evaluation. We cover 4 metrics. We first look at the coverage of my tool, then the correctness, the performance, and lastly, the downstream program analysis. Coverage, we gather some metrics for this. We gather the initial annotations that are present, provided by the developer, also annotations that are inferred by Python, but also annotations after running my tool, and some information regarding type slots. This is enough, we also gather some more, but this is enough for coverage. Next is correctness evaluation. You might wonder, why do we do this? Well, for example, if you originally have a function that's annotated with float annotations, and now we strip away these annotations, run my tool over it, and it fills in these integer values. Honestly, they are correct in the context, because an integer is a subtype of a float, but it does not match up with the original ones. So although it's valid, it's not correct. For this, we have 2 accuracy metrics. We have adjusted accuracy and base accuracy. The adjusted accuracy filters out all type annotations that are none and any. And we can also convert fully annotated, fully qualified names to simple names. So you could have an annotation like torch.answer, which could become torch. And we rewrite some things. And lastly, base accuracy is the same as adjusted accuracy, except we only check for the outermost type. So the list integer matches the list part of this, but not, for example, if it is a sequence of integers. For the performance of my tool, we also gather metrics, for example, the time taken for each step and the peak memory used by it. And lastly, we would also like to investigate the impact of type annotations on downstream program analysis. For this, we use call graphs, and my professor works at a company called NLabs, and they allowed me to use their NLabs call graph generator tool, which is very nice, because I'll show you. If you have code, and you run a tool over this, you can generate a graph. For example, we start at A, and then we have an if condition, so we can go to B or to C. And from C, we can also go to E or F, but ultimately we end up at D, creating a graph like this. This is useful for the practical use case of these type annotations, because we suspect that adding type annotations to code will actually make the call graph more precise. And how? Well, likely by removing edges. So, these are my evaluation. This is my evaluation strategy. Now for the results. We start with the type for Py model. Type for Py, the results were collected for 16 projects. Quite popular Python projects like Django, Flask, and Matplotlib, and some general information was gathered on the coverage. For example, over these 16 projects, on average, there were 41 time slots per file. Of these 41 slots, 17 were fillable, so not yet filled. Then, after running PyWrite, we have 13 unfilled slots, so it added like 4. And after running my tool, this number gets even lower to 5. So my tool indeed filled in more type slots. As for the coverage, I would like to show, especially PyWrite with the added annotations, which is 21 to 61%. But now, after running my tool, after PyWrite, we add an additional 62% more type annotations to the code. And if we start off originally with the project, which isn't run, just the code given, then the number of unfilled type slots, well, there are some. And we expect that if we run my tool, the slots get filled, so the number of unfilled type slots decreases. And you can clearly see this in this diagram, where the distribution moves to the left, where the number of unfilled type slots, well, there are fewer. As for the correctness, well, originally in the code, on average, there were 17 type annotations provided by the developer. Now, we strip these out, we run the PyHintSearch tool, and we add 12 annotations back. Now we can compare these. Of these 12, 4 were correct using the adjusted accuracy, and according to the base accuracy, it were around 5. So the precision for type for pi is around 1/3, or 0.43% for the base accuracy. As for the performance, PyHintSearch's total time over all these 16 projects, for using the top 1 search tree, it was 13 hours and 45 minutes, and well, the more annotations you use, the larger your search tree becomes for the search, so the time increases. From this and the previous slides, we can see that using the top 1 actually provides the most annotations, also the most accurate annotations, and it is the fastest. As for memory usage, well, PyHintSearch uses around 120 megabytes of memory, and its scalability, well, there's a hard limit of 100 fillable type slots after the PyWrite step. So if PyWrite has run, and there are more than 100 type slots that can be filled, it's just inconvenient, and we skip those files. Everything underneath the type 100 mark is still explored. And why, you might ask? Well, if you have 100 type slots, often functions are dependent on one another, and if a function is dependent, then we need to backtrack more often. And if you need to backtrack, then you search an exponential number of combinations once again. You hit the timeout limit of 5 minutes per file that I've built in, otherwise you search possibly for hours, and well, that's the scalability of it. Now, for the call graphs. I ran it over the 16 projects. I'll show you the results of one. If you have the original code and you run it through the call graph generator, you have the existing call graph. If we annotate the file after my program, we have the new call graph. These call graphs can be compared for their edges. Some are the same, some are added, some are removed, and primarily the removed edges are very nice because, well, then we make the call graph more specific. Let me show you. We have a function, an init function, and now we specify that the data parameter is a dictionary. Because we specify this, 13 generic edges related to a keys function are now removed. For example, these more generic ones. And you could also see that some edges were actually added. Why is that? Well, another function that is annotated with a list of objects and a generator. For these, once again, generic next function edges were removed because of the more specific type annotation. But hey, because we also specified a list, we added 2 more specific edges, like the build-ins.list. and well, next, for example. It became more specific. Nice. However, sometimes it happens that the annotation that we added is actually incorrect. And this is not very good, because an incorrect annotation, you can see that here the string parameter, which was originally in the function implementation cast to a list, is now regarded as a text.io object and not as a list anymore. And now because it's not regarded as a list anymore, 10 generic pop function edges were added instead of the one that was originally just the pop function for a list. Okay, so we discussed type for pi. Next up is type T5. Type T5, the results were collected for 4 projects, namely Bleach, Colorama, Requests, and Seaborn. But why only 4, you might ask? Well, this was because of the extremely long prediction times of the type T5 model, and I'll get to that. I'll get to that later. Well, once again, the general information for each file. On average, there were 43 type slots. Of those, 20 were fillable. After PyWrite, 16 were left unfilled. But after my tool, well, if we use the type for pi model, around 5 annotations were not filled. But using type T5, this value even decreased further to 3. So it is a more accurate model. As for coverage, well, once again, the most important values are highlighted. After the PyWrite inference, we run the PyHintSearch tool, and now we see that with a type for pi model, we add 65% more annotations, but the more accurate type T5 model can actually add even more type annotations, almost 80%. For the correctness, well, originally there were 26 annotations. After stripping those and running the tool, we now add 16, or 17 for type T5. Of those, we can compare the correctness, and we see that type T5 has more correct annotations added than type for pi. This also improves the precision, where originally it was 1/3, we now have half of the annotations that are added are correct. And for the base accuracy, it's even higher, going up to 0.6 precision. Now, I mentioned the performance. Type T5 has some slow predictions. For example, the Bleach project took around 5 minutes to compute the predictions, and then we still need to do the search. But Seaborn, which is a 5-fold increase in files, scaled much worse. It took 175 minutes, or almost 3 hours instead of 5 minutes. And well, then you have these other files like projects, like Pandas and Stripe and Django, which consist of hundreds of files. And when I tried running it, it just didn't work. It took way too long, and even my Flask API timed out. So, over these 4 projects, we ran PyHintSearch, and both with the type for pi model and the type T5 model. And type for pi took around 48 minutes, whereas type T5 took 4 hours and 7 minutes, much longer. As for memory, well, fairly similar actually. The PyHintSearch step with type T5 took around 120 megabytes once again. As for scalability, well, things are still the same compared to type for pi. There's still this hard limit. We still do backtracking if there are too many if there are too many annotations, but only type for pi only provides a single prediction. So the tree is smaller, so we have less exponential growth, and thus we can also backtrack faster throughout the tree without because there are fewer. It is less wide. There are fewer annotations to check. So, to conclude, what is the first research question that we would like to answer is, what is the overall increase in the number of type annotations when combining static type inference with a machine learning model? Well, if we just run PyWrite, around 21.61% more type annotations are added. Now, if we run MindTool, then we improve over PyWrite. With the type for pi model, we add 62.45% more annotations, and with the type T5 model, it's almost 80%. So, nice. The second research question is, what are the performance characteristics in terms of speed, memory usage, and the scalability of the tool? Well, type for pi was basically throughout most of the research the default model, and because it has 16 projects, I'll discuss this one more. The total time taken is 13 hours and 45 minutes, and this is the division, and the peak memory is almost 120 megabytes. As for scalability, well, it's actually dependent on the accuracy of the machine learning model. If you have accurate annotations by a model, we can fill these type slots from top to bottom linearly. Each type slot, we have n from the top n predictions, and if we try those, and those fit in the type slot, then we just linearly go through the program. However, if we have not so accurate annotations, then there is an increased chance of backtracking for the functions that are dependent on one another. This leads to exponential execution time and often hitting the 5-minute timeout per file. Lastly, the use case. How does the presence of type annotations impact the downstream program analysis? Well, it turns out that indeed type annotations provide additional information to this call graph generator. However, if we provide incorrect type annotation, we add edges which are related to more generic functions. So that is not really what we want. If we do add the correct type annotations, then it's very nice. We remove edges related to generic function calls, and we actually add edges to more specific function calls, thus making the call graph more precise. Now, for future work. My thesis included this search tree with a kind of depth first search through it, but there is also another alternative where we have a genetic algorithm. Genetic algorithm, you have a population which you try to evolve and mutate, and then you try to fit it to a fitness function, and with this you can also try to find a combination of types that can be added to your program. As for improvements to the tool, well, we could send partial file changes. Currently, we have the contents of a file, and if we try to add a type annotation to it, we send the complete file changes, the complete content that is changed, instead of just sending the line where the change actually happened. Well, It is uncertain if the validation results actually come back faster if we just send a partial file change, but it could be a possibility. Also, we could have decreased memory usage because currently when we try to backtrack, we keep an array of trees that represent basically my program. And for each time we need to backtrack, we just go to the previous version of the tree. However, now we are just storing large trees in an array, and we could also just store the initial tree with all the modifications made to it, like the type annotation that is added at this specific slot. Lastly, we could also specify a minimum probability threshold. For example, if you have an annotation that is predicted, but just has a 10% chance to actually fit inside of the code, well, then we might also set a threshold, like 50%, that everything underneath that, we just do not assume that we are going to try it, because it has such a low probability of actually fitting in the code. Therefore, we reduce also the number of annotations that are checked throughout the search, and I would say this is also a useful improvement to the tool. With this, I would like to conclude my presentation. Thank you very much for your attention, and are there any questions?